welcome back. We are still on section 1. There's a lot to accomplish here. We're looking at subsection 4. We're talking about modeling functions using proportionality. So there's a couple of review objectives kind of tucked within this. One is to express a relationship between two variables related by proportionality, and another is to write a mathematical expression defined in words by sum, difference, product, quotient, so all of our normal arithmetic stuff, adding, subtracting, multiplying, dividing. These are called review objectives, but depending on where you took a prerequisite class for this, an intermediate algebra class or an algebra 2 maybe in high school, these might not have been covered super in depth. So I always try to talk about these with a little more thoroughness than I might some other prereq topics. So we've got a couple of common ways of expressing proportionality. One is sometimes called direct proportionality. So I'll make a little note here. You can sometimes squeeze that word in there, directly proportional to. So Q is proportional to T if there's some constant, so that you can write this expression, this equation, as Q equals that constant times T. And that's got to be true for every combination of T's and Q's in order for this statement to be true. So it can't just be some combination that happens to work. Otherwise, pretty much any numbers could be proportional to another number. So got to always be the case. Kind of the flip side of that, no pun intended, is inversely proportional. So Q is inversely proportional to T if it looks the same almost. So the only difference you might notice is that instead of K being multiplied by T, now we're dividing. So the variable component's on the bottom, and again this K has to be the same constant no matter what for any combination of Q's and T's. So just as a quick example, I know it's always hard to be looking at these in the abstract, but we would have, for instance, for direct proportionality, we'd have something maybe like Q equals 5T. And then for inverse proportionality, you can just, pick your own constant. I usually ask my class to just give me one so I can illustrate that it's really nothing fancy. 7's a good number, so we'll make our constant of proportionality be 7. Okay. So slightly more interesting, involved, complicated, pick your adjective way of approaching this is when we combine these two things. Because if we just say variable 1 is proportional to variable 2 with this constant of proportionality, there's not a lot of mystery, not a lot to put together there. So we will tackle one with a little more depth. So we're going to pick different variables just to keep things extra annoying. So write a formula for G as a function of P. And again, I'm going to stress this this substitution idea that is so of principal importance in math, that as we read through this stuff, then likely what will happen the first time you read through it, you get almost nothing out of it. And that's just the way it is with really dense subject matter. That's true at any level of student all the way up through professors. You're going to have to kind of dive into this a few times. So you read through it once, expect to kind of get a brief idea of what's going on, but once we start digging down and identifying these pieces we can translate, then we can start to actually make some progress and use that substitution strategy. So if we're supposed to write a formula for G as a function of P, we're going to assume that G is proportional to the product of these two things, P and 1 minus P, and then we have a constant of proportionality 1.5. So again, most humans make it through that sentence and basically just ask themselves, what did I just read? So now maybe we revisit and we start to try to piece some of this stuff apart. So we're going to get a formula. Great. It's going to be G as a function of P, and maybe that's kind of the first solid mathematical piece that we can tease out of this. So we might say G as a function of P, so our goal is going to be something so that G looks like f of P. There's our first hint at what we might be up to here. So then we keep going. We're going to assume that G is proportional to the product of P and 1 minus P. So there's another element that is going to help us out. This is the direct proportionality situation, not the inverse proportionality. So we're going to be working with our first definition up top there. And gosh, all right, so it's proportional to, well, it couldn't just be easy and say x or something nice like that, but proportional to the product of these two things. So I'm going to start writing equals k times something or other, because that's what this underlined yellow component basically gives me so far. G is proportional to something or other. Eventually I'm going to run out of colors here. Let's pick this nice lavender again. So now we run and do another piece of math terminology that's useful. So the product of two things. So we have these four common words in math that kind of translate to our arithmetic. We have the sum of things, which is addition. We have the difference, which is subtraction. And then we have ratio, which is division, and product, which is multiplication in this case. So when we see the product of two things, I guess what I'm going to do is I'll kind of see the writing on the wall and make some space for what's about to come. But product is just giving us two things getting multiplied together. Product is just the results after we multiply. And then the two things that are supposed to be getting multiplied here are p and 1 minus p. I guess fine. Maybe we've got some parentheses going for us, but other than that, that's the best we can do. P times 1 minus p. And then the last thing here, this is a pretty decent formula, except that it still has this unknown constant k. So just to round out the last little bit of information that we could possibly squeeze out of this very detailed sentence, constant of proportionality 1.5 is going to give us the value of k. So when all's said and done, we can maybe get rid of some of the color because it kind of looks like a kid threw up a paint palette all over this. We've got k, which was 1.5. We've got p. We've got 1 minus p. Fantastic. So again, we have all of these little underlined pieces are just us taking small components of phrases, things that we have definitions for that we can translate into some kind of mathematical expression and writing them out. So we see once more, this pretty concise little formula here has packed all of this information from that sentence and down into it. But Mike, where are the word problems? Said no math student ever, probably. So we have, we had to deal with words here because we had to do some translation. But one of the really interesting applications of this actually came from a TED Talk from a while back. And it wasn't a TED Talk about math at all. It was what is his name? Jean-Baptiste Michel. So he was talking about regularization of verbs. So I guess this is how the example here is you take a regular conjugation of some verb. So I think, he thinks, she thinks, and you look at, say, past tense. At some point, English, and I don't know when, there's people who are much more knowledgeable about this than I am, English switched to I thought, to this kind of irregular way of conjugating this. As opposed to what the regular version would be, which is I thinked, which of course is not proper. And that this happened over time, and what he observed was that the more these words were used, the greater this frequency was, the faster these words became regularized. They stopped having these weird conjugations and started being kind of what everybody expected them to be. And so the big reveal there, at least with my math brain turned on, was he found that this rate of regularization was inversely proportional to the square root of that verb's frequency. So again, there's a lot of stuff here. You'd be forgiven for thinking that you accidentally walked into your writing composition class and it's time to find a different video to watch. But this was kind of a nice little neat mathematical nugget that was tucked into this TED Talk. So our task is going to be, our first one anyway, write a formula which gives that rate of regularization as a function of its frequency. And again, you read that sentence that's telling you something to do, you probably have no sense of upon that first read of what it is we're trying to accomplish. So we'll go back through, take it a little slower, and see if we can piece out some of these elements. So again, we're writing a formula, so we know the end result is going to be some kind of equation. We're supposed to give the rate of regularization and rate of regularization as a function of something else. So basically, all I'm going to try to do is underline the phrases that are on either side of as a function of. That's sort of the connective tissue of this set of instructions here. So something as a function of something else is a really common phrase we're going to see an awful lot in this class. And the great thing about that is it's really consistent in the way that it's written, so that the first component, the thing that is as a function, this is going to be our output or our dependent variable. And so that's giving us some structure to work with in our equation. And then the second component is always going to be this input, or the independent variable. And that doesn't look like a word. Okay, so we're starting to kind of compress this from words, and I almost literally picture like some Play-Doh where we're sort of mushing this stuff into shape from the kind of block that it is right now. So far we know we've got a formula. We're going to be able to write this as some combination of these inputs and outputs, and we'll settle on blue. So our goal, again, some kind of formula. And the other nice thing about having words, or maybe the annoying thing, depending on how you approach this, is nobody's told us what these variables have to be. Nobody's given us letters that we have to use for this. It's entirely up to us. So we could go the uncreative way and pick X's and Y's, but I resist. I'm going to try to pick some letters that actually help remind me what these things represent. So for instance, rate of regularization, gosh, that's got a lot of R's in it. I think maybe my most tempting choice would be to call that output R. And then this is some function of, well, I've already sort of messed things up, because the logical choice would be to call frequency of use F, but I've already used F as the name of a function. Can't repeat letters like that. So maybe we'll just use U for its use. But again, it's entirely up to us. You can pick whatever you want. All right, so we've got the barest framework for this. If all we had was what was written in part A here, we would sort of be done. We'd have nothing else to go off of except picking some variables and then going on with our lives. Well, that might be exactly what you want right now. It turns out we've actually got enough information to make some more progress with this. So going back up to this fairly lengthy explanation of what this guy found in this talk, this last sentence is kind of a gold mine as far as instructions for how to proceed here. So we have mathematically, great, don't care about that. He found that and here's where I really just kind of want to enable my pattern matching brain. Here is rate of regularization down here, and rate of regularization appears up here. So even if these were just gobbledygook words, which they may feel like at this point, honestly, I can see that they're the same thing. The rate of regularization is the same between these two phrases. So whatever's going on there, it's referring to this same variable. So we've got our R, and then that was inversely proportional to. There's another great little piece of this sentence that we can extract and turn into something mathematical. So I'm going to use that for our lavender here and say what we've really come up with is basically that this equation has to look like inversely proportional to means we have some constant divided by whatever our, well, actually I'm going to hold off on that because we've got the rest of the sentence. It's this constant divided by something interesting. And then the rest of the sentence says the square root of the irregular verb's frequency of use. Yikes. Also a mouthful. But it's a familiar mouthful because it's the exact same expression that appeared down here. Frequency of a verb's use, frequency of use. So we've got square root of verb's frequency of use. Wonderful. So this is pretty close to just that variable, but not exactly yet. We've got not just u, but the square root of u, which is actually great. So here is our final formula written without any color, just so we have something finalized there, and we'll reward ourselves with that fancy box of completion. Again, we were kind of reassured in this last part here, your answer may contain an unknown constant. That seems to be what's going on with k here. So here's our rate of regularization, how fast verbs that have these weird conjugations turn into the thing we would expect, and this is our variable u for how often that word is used. Okay, last piece, we're going to try to give ourselves enough information that maybe we get ourselves an honest-to-goodness function out of this, that we don't have to worry about this silly little constant lurking up there. We can actually get something that, if you know how frequently a verb is used, then we can figure out how quickly it will be regularized. Okay, so we have a little snapshot here. So we have a particular irregular verb, and its frequency is 10,000 uses per day, however we might measure this. And it regularizes at a rate of 1 over 100,000. Again, we could kind of make up whatever fanciful units we might want out of this, but as long as we're consistent, the numbers are kind of the most important facet. Okay, our goal, find the value of the constant and rewrite the function using this value. So great. I think we have a fairly concise goal in mind, and that is to get ourselves a formula. Goal. Find k so that we can write that equation from up above without any unknowns in it. Okay, so what we've actually been handed here takes sort of a second to piece through, but basically we have been told an average frequency, and we have been told a regularization rate. So if you look back at what possible things this 10,000 could refer to, remember frequency is a variable that we have. So some things that we know that this is basically telling us for some word out there, frequency is 10,000. And for that very same word, we know the rate that it regularizes, whatever that means. This is another piece of information we know, and it's even better, a variable we've already defined. It's this r thing. And then maybe if you're like me, you kind of get that, you sink into that slightly comfortable sensation of actually having an equation to work with and not just a bunch of words to sort of float around. So we started with our equation from A. So we had r is k over square root of u. And this gives us a little snapshot, basically an ordered pair, if you like, an x and a y. And when we let the actual variables in this formula take on those numbers, you might notice the only thing we don't know at that point, with r equal to 1 over 100,000 and u equal to 10,000, the only thing we don't know is that k. And that's fantastic. One equation, one unknown. We got a pretty decent shot at putting that together. Okay, so variety of approaches you could tackle first here. They all end up with the same result, but even if you implement my favorite everybody hates fractions policy by making these things go away, then that'll do it. These are numbers though, so you could just kind of right away decide that what you wanted to do is grab a calculator and get some values for each of these sides. But either way, square root of 10,000 should be 100, and then we're multiplying by 1 over 100,000. And the whole point of doing this mess on the right side was so that that piece would go away, and we should just be left with k. Mathematicians would be pretty satisfied with that as a number, but I think most humans would rather get down to a decimal, and I think we're looking at 1/1000th. So this was the principal kind of algebra thing that we wanted to put together. Then to just round everything out, the goal, if you recall back to our actual, no, I don't want to turn Wi-Fi off. Our actual goal here was to find the value of the constant and rewrite the function equation. So we can put it all together. Got our constant, and so now our equation looks like so. So that, remember, because these two variables are inversely proportional, then this constant is the same no matter what other combination of variable values we might pick. So having that one little snapshot that we did up above enables us to get a formula for this for any other combination. Lovely. Okay, We'll be back with some more functions in the next section.